In this lesson, we will discuss functions of a complex variable. So far, we've been developing the basic theory of complex numbers. Now we will turn our attention to functions of complex numbers. So complex valued functions are defined in a similar way to functions of real numbers that you may have studied in calculus. The only difference is that they operate on complex numbers rather than real numbers. So a complex valued function f of the complex variable z is a rule that assigns to each complex number z in a set S exactly one complex number w. So we see this definition is very similar to one you might have seen when you studied real valued functions. So we write w equals f of z, and we call w the image of z. Now we defined a function f of z on a set S. S is going to be known as the domain of definition of the function f, or simply the domain of f. And the set of all possible images so that is the set of all w equal to f of z such that z is an element of the domain of f. This set is called the range of f. So just as we expressed the complex number z by its real and imaginary parts, we can also break up a complex valued function into its real and imaginary parts. So given a complex number z, we can write w, which is f of z, as its, and we can break this up into its real and imaginary parts, u plus iv, where u and v are the real and imaginary parts of w. So u and v will be real valued functions that depend on the real variables x and y. So u and v are real valued functions of the real variables x and y, So we could write w, which is f of z, and z is x plus iy. So we think of u as a function of x and y, so u of x comma y, plus I times the imaginary part v, which is also a real value function of x and y. So we can break up any complex valued function into its real and imaginary parts. Let's look at an example of a complex valued function. So let's let f of z be defined by the formula z cubed plus z plus 1. To break this up into real and imaginary parts, I'm going to write z as x plus iy, and we see that this will equal x plus iy quantity cubed plus x plus iy plus 1. And when I cube the term x plus iy, I get this expression, x cubed plus 3x squared iy plus 3x iy quantity squared plus iy cubed plus x plus iy plus 1. And when I simplify, I squared is equal to minus 1 and collect all the real parts, I'll end up with x cubed minus 3x y squared plus x plus 1. And then when I factor out a factor of I from the imaginary parts, I get I times the quantity 3x squared y minus y cubed plus y. And so therefore I can write u of xy, the imaginary part of f of z, as x cubed minus 3x y squared plus x plus 1, and the imaginary part of f v of xy is 3x squared y minus y cubed plus y. So breaking this function up into real parts and imaginary parts will be useful later when we start talking about differentiability and analytic functions. We've seen how it can be useful to write z in polar coordinates. So similarly, if we want to write a function f of z in polar coordinates, so the polar coordinates r and theta are used, then we can still break up f of z into its real and imaginary parts. Now u will depend on r and theta, and v will also depend on real numbers r and theta. So for example, we had f of z equal to z cubed plus z plus 1 in the previous example. We can write this in polar coordinates as f of r e to the I theta. So r e to the I theta cubed plus r e to the I theta plus 1, and I can distribute the power of 3 into this product in the first term. Then using Euler's formula for e to the I theta as cosine of theta plus I sine of theta, we can break this up into real and imaginary parts, and r cubed e to the I 3 theta would be r cubed cosine of 3 theta plus r cubed I sine 3 theta. And then r e to the I theta would be r cosine of theta plus I r sine of theta plus the number 1. And then combining the real parts, I have r cubed cosine of 3 theta plus r cosine of theta plus 1 plus I times the quantity r cubed sine of 3 theta plus r sine of theta. So then the real part of f is u of r theta equals r cubed cosine 3 theta plus r cosine theta plus 1, and v of r theta would be r cubed sine 3 theta plus r sine of theta. For the next example, let's let f of z be given by the formula absolute value of z squared. So writing this in components, this would be x squared plus y squared, which is always a real number. So this function has real part u of xy equal to x squared plus y squared, and imaginary part equal to 0. So this is actually a real valued function. So the outputs f of z are always real numbers, so it's a real valued function, but the inputs are complex numbers. So it's a real valued function of a complex variable. F takes complex numbers and sends them to images in the real numbers. So polynomials will be an important class of functions, of complex valued functions. So we've already seen an example of a polynomial. So let's define a polynomial for complex numbers a0, a1, a2, up to an, with an not equal to 0. We define the polynomial p of z equal to a0 plus a1z plus a2z squared all the way up to an z to the power n. Call this a polynomial of degree n. So we see that the domain of definition for any polynomial function will be the entire complex plane. When the domain of definition is not mentioned, the largest possible set is going to be taken as the domain of definition. When we take a quotient of polynomials, we get a rational function. a rational function P of z divided by Q of z is a quotient of polynomials P of z and Q of z. So the domain of definition for any rational function will consist of all complex numbers such that Q of z is not equal to 0. Complex valued functions can also be referred to as mappings or transformations. When we study properties of real valued functions, it's often useful to examine the graph of a function. With complex valued functions, however, we cannot easily graph these functions since the inputs and outputs each lie in the complex plane. So we can't easily graph w equals f of z since z doesn't lie on a line like a real valued function. Z and w each lie in a plane. So what we can do, instead of drawing a graph of f of z, we can draw two planes, a z-plane and a w-plane, and indicate how pairs in the z-plane get mapped to points in the w-plane. So instead, we can draw z and w planes and indicate pairs of points corresponding to inputs and outputs of the function. So when we think of f in this way, f is usually called a mapping or transformation. So as an example of how we visualize complex valued mappings, we take points in the z-plane and look at their corresponding image in the w-plane. So we have u equals the real part of w axis and the v axis, which is the imaginary part of w. And we have a correspondence where z0 gets paired up with a point w0 in the w-plane given by the definition of f. So let's look at some examples of elementary functions that map points from the z-plane into the w-plane. So let's first look at the mapping given by the formula w equals z plus I. So z as x plus iy gets sent to x plus I times the quantity y plus 1. So see that any z in the z-plane will be translated to a point in the w-plane that is 1 unit higher. So this function is called a translation. This is a translation of each point z moving up 1 unit. So if we take a point z0 in the z-plane and map it to a point in the w-plane, the point z0 would correspond to the point w0, which will be z0 plus I. So you see that the point z0 gets shifted up 1 unit in the complex plane. Let's see what happens when we multiply by I in the complex plane. Let's look at the mapping given by W equals IZ. We saw earlier that complex multiplication can often be best understood in terms of polar coordinates. So I'm going to write W equals IZ in polar form. I is given by e to the I pi over 2, and I'm going to write z as r e to the I theta. Then multiplying by I, we see, is going to result in a rotation, because when we combine theta and pi over 2, we get r e to the I theta plus pi over 2. And we see that the original point z gets rotated in the counterclockwise direction by pi over 2 radians. So to visualize this, imagine we had a point z0 in z-plane, z equals r e to the I theta. Then this point has a vector r of length r associated with it and angle theta. Then under the transformation W equals IZ, we see that in the W plane, the original vector will, with angle theta, will be rotated in the counterclockwise direction pi over 2 radians to this vector, still with length r, but now argument theta plus pi over 2. So we see that multiplication by the complex constant I results in points rotating in the counterclockwise direction pi over 2 radians. Our next example is the function w given by the conjugate of z. So the point x plus iy would be sent to its conjugate x minus iy. We see that this actually transforms points it'll transform the point z equals x plus iy into its reflection across the real axis. while it can be useful to look at the images of points through transformations, we can often gain more information from sketching images of curves or regions. So let's revisit the function w equals iz. This function will map a line given by the equation y equals x plus 1 in the z-plane it'll map this line onto another line in the w-plane. The line v equals negative u minus 1 in the w-plane. So to see this, let's write u plus iv as w, and w equals iz, and z is x plus iy. So when I multiply through by I get a minus y plus ix. So from the correspondence u equals iv, from the equation u plus iv equals negative y plus ix, we get that u equals negative y and v equals x. Then the equation y equals x plus 1 becomes negative u equals v plus 1, which is equivalent to the line v equals negative u minus 1. So to visualize this transformation, let's look at the graph of the line y equals x plus 1 in the z-plane. And we already looked at the transformation w equals iz as a rotation counterclockwise by pi over 2 radians. So we can see that the graph of v equals negative u minus 1 in the w-plane this graph would look like this line, and we can see that this also corresponds to a rotation of the line y equals x plus 1 counterclockwise pi over 2 radians. Next, let's look at the transformation of the rectangular region shown in the first quadrant here, with corner at z0 equal to r e to the I theta under the transformation w equals iz. We see that this rectangle will be rotated pi over 2 radians counterclockwise, and so we would end up with the following. So the image of z0 would be w0, and we see that it's like taking the rectangle and standing it up on its edge. So now let's consider the polynomial function w equals z squared. So if I write z in polar form, we have w would equal r squared e to the I 2 theta. And so we see that the point z would be mapped to the image found by squaring the modulus. So the point would be the distance r squared from the origin, and the argument would be doubled. So the image of any non-zero z is found by squaring the modulus and doubling the value theta of the argument of z. Let's look how a region will be mapped under the transformation z squared. So imagine in the z-plane I had a wedge-shaped region where this angle theta is pi over 4, and let's say this length is 2, so the point on this corner of the wedge is z1 equal to 2e to the I pi over 4. So let's see how this wedge shape would be transformed under the function w equal to z squared. So in the w plane, the point 2 on the real line would be sent to the point 4 in the w plane. So at 4, this would be the point w0, the image of z0 equal to 2. And the point z1, which was 2e to the I pi over 4, would get mapped to w1 which is given by 2 squared, which is 4, times e to the I pi over 2. So we double the argument. We get this piece, it's like quarter of a circle. So now we have this original wedge being transformed to the quarter of a circle centered at the origin with radius 4 in the w plane. So let's think about what set in the z plane would be mapped onto the upper half plane of the w plane. So since this mapping squares the modulus, we see that w equals z squared would map the first quadrant given by r greater than or equal to 0 and argument theta greater than or equal to 0 and less than or equal to pi over 2. You take this first quadrant in the z-plane and it would map it onto the whole upper half w-plane. Next, we'll look at transformations of an elementary function that is not a polynomial. Let's consider the exponential function given by w equals e to the z. So z can be written as x plus iy, and then by using exponent properties, we can factor out e to the x and write e to the z as e to the x times e to the iy. So under this transformation, the vertical line x equals a so if x is always equal to a constant a, then the quantity e to the x will be equal to the constant e to the a, and so points on the transformation e to the z will all have the same modulus e to the a. So we see that the line x equals a is mapped onto a circle centered at the origin with radius e to the a. So the vertical line x equals a would be transformed under this transformation e to the z onto the circle in the w plane centered at the origin with radius e to the a. And if I were tracing out the vertical line x equals a going from the bottom up to the top, then the corresponding points on the circle would be mapped out in the counterclockwise fashion. So vertical lines get transformed into circles. Let's look at the set of points on a horizontal line under this transformation. So the horizontal line y equals b. So if the value y is constant, then the points on the image of this horizontal line would all have the constant argument, and therefore we see that the horizontal line y equals b is mapped onto a ray given by phi equals b. So the angle in the w plane is radian measure b. So if I draw a dotted horizontal line y equals b, then this line would have image equal to the ray starting at the origin and going out infinitely away from the origin, and this angle that this dotted line makes with the u-axis would have radian measure b. And if I followed this line horizontally from left to right, then the ray would go from 0 to out to infinity. So now that we know how e to the z maps vertical and horizontal lines, let's see the image of a rectangular region in the z-plane So let's say that this vertical line is at x equals a, and this edge is on the line x equals b, and heights of the horizontal edges are at heights c and d. Then under the transformation e to the z, we would get this image, which is sort of a slice of a ring, and this angle would be measured by phi equals c, and the radian measure of this ray would be phi equals d. So let's look at the corresponding images of the edges of the rectangular plane. So the edge going from height c to d on the vertical line x equals a would get mapped onto this part of this arc, the smaller arc closer to the origin at radius e to the a, and then the other parallel side would get mapped to the larger arc, and the lower horizontal edge would get mapped onto the ray with measure c, and the final edge would get mapped onto the ray with angle measure d. Let's look at the image of one more region under the transformation w equals e to the z. Consider this infinite strip bounded between the horizontal line y equals 0 and y equals pi. So the boundary would get mapped to a ray in the w plane with argument equal to 0. So we see that the real line in the z plane would get mapped onto the ray starting at the origin and going to the right forever. And then the horizontal line y equals pi would get mapped to the negative real line in the w plane. And so we see that the image of this horizontal strip where y is between 0 and pi gets mapped to the upper plane, v greater than or equal to 0 in the w plane.